Let's see if I can make this work for us. I will be working through a few of the chapter review problems. So the first one here I'm going to do is number 9. So it says the sled traveled at the speed of... So number 9. I'm going to write out our given information. And what's given to us in the problem is that the sled is traveling at a speed of, so v is equal to 3.0 meters per second. And it's slow, so this is v initial. And it slows to a stop, so delta x is that it went 4.0 meters, where its passengers rolled off. What is the magnitude of the horizontal net force that slowed the 110 Newton force sled? So force weight is 110 newtons, and we know gravity is 9.81 meters per second squared. Alright, so let's draw our picture. We have our flat surface. My sled is going to be just a bucket here. Sorry. Okay, I'm going to change my color just to show that the sled is actually traveling. Oh, yep, that didn't pan out, did it? So, v of 3.0 meters per second. And it travels from here to here. This is 4.0 meters. Alright, so what is the force that caused it to stop? So we know that the force weight is moving it forward. And we've got the force weight on the sled. Oh my goodness. Come on. That's what I have to do. Alright. So force weight is mass times gravity. And so we know that the force weight is 110 newtons. And 110 newtons times mass times 9.81 meters per second squared. We can solve for the mass of this sled. So we're going to take 110 divided by 9.81. And that gives us, with 2 sig figs, 11 kilograms for this sled. Remember, the SI base for mass is kilograms. Alright, now we are going to obviously be having Kelly speed, so this is stopped at this where the passenger rolls off. Let's see. So what we were actually looking for is a force this way. So we're just going to call it force applied. Okay, and we're going to have the force that's moving it forward is essentially its momentum, and we're going to know that we're obviously going to find the net force is equal to mass times acceleration. And we're looking in the x direction. So force applied being the only force, we'll have a mass. We should probably find its acceleration. We were given a force of the initial, and obviously if it comes to a stop, we know that the v final is going to be 0 meters per second. So acceleration, remember this is one-dimensional acceleration, so we're going to find acceleration is equal to v final minus v initial divided by time, but we don't know time. So let's use a kinematic. It's a constant acceleration. I don't have my kinematics with me. All right. So if we look at our note cards, and we're going to find probably the time-independent kinematic, and it is that V final squared is equal to V initial squared plus 2 times acceleration times delta x. So we know V final is 0 squared. V initial was 3.0 meters per second squared. 2 times the acceleration we're solving for times delta x, which is how far we went, which is 4.0 meters. Alright, so let's solve for a. We'll take 3 squared and get a negative 9 over here. Equals 2 times 4, which is 8 times a divided by 8 divided by 8. So a is equal to, and that is meters on bottom. So one of the meters crossed off, which would be meters squared, crossed off there. So it's just meters per second squared is what we end up with. So 9 divided by 8 gives me a negative 1. Sig figs, 2 sig figs, 1 meters per second squared. All right. So now I know my acceleration. I'm thinking back to Newton's second law here. My net force is literally going to be what my force applied is, because there is no force actually acting on the object there. The reason it's moving is because the acceleration that already existed and the mass. So if we plug in what we know, what force applied is will be the only force in the x. So we know that that force, I'm going to change my colors just so you can see a little bit different. So my summation of forces in the x is equal to my force applied by itself, which is equal to my mass, which I found to be 11 kilograms, times the acceleration, which I just found to be negative 1.1 meters per second squared. So 11 times 1.1 gives me a force applied 12.1 newtons negative. I think the answer key said 13. And the reason they got that is because they probably kept all their numbers on their calculator again. So if we were to run that without doing the sig figs, we would end up with one closer to 13. But I just got 12 newtons by doing sig figs each time, and it would be a negative 12. If you ever get a question like this on a test, just ask me and make notes. But 13 is obviously the closest to that number, so. All right. Let's move on. I'm going to try to save this recording first. So this was